Hey everybody. So in the last video, we were able to work out the following derivative. The derivative of the natural exponential function e to the x is just itself e to the x. So we're gonna now take a look at the natural log, right? So the first thing we have to remember about the natural log, I've got a graph of the natural log up here. If you don't remember what that looks like, is it is the inverse function. The natural log is the inverse function to the exponential function, okay? So what does that mean? If I have y equals the natural log of x, this means, right, the definition of this inverse function is to say that e to the y is equal to x. All right, that's what it means for this to be the inverse of that function. So we're going to use this definition, right, to come up with the derivative. We're going to take the derivative of both sides of this equation with respect to x. Okay, so on the right-hand side, this is simple. The derivative of x is just 1. On the other side, let's do a little scratch work over here. We have to remember something. Y is a function of x. So we're doing an implicit differentiation here, right? Which really means we're using the chain rule, right? That I have two functions here. I have, so let's write it this way. Let's call it f of g of x, where f of x is our exponential, and g of x is some function is y, right? We know it's natural log, but we're just calling it y for now, right? So y prime, or sorry, f prime of x is e to the x, and g prime of x is just y prime. Right? That's what that thing means. So putting that into here, into our chain rule, we're going to get f prime, which is e to the, not x, e to the y, times g prime, which is just y prime. So we get e to the y times y prime, okay? Or dy dx. So now I can just rewrite this as y prime is equal to 1 over e to the y. But according to our original relationship, we know exactly what e to the y is. Y prime, 1 over e to the y, but e to the y is simply x. And that is the derivative of our function, okay? The derivative of the natural log of x is equal to 1 over x. All right, so this is another nice result. It's not quite as nice as the exponential function that has itself as a derivative, but for the natural log, which can be, you know, a fairly complicated function to understand sometimes, this is a pretty straightforward derivative. Let's take a look at this. So here is, remember, the natural log has as its domain only positive numbers. That's implied, right? So we're looking at the derivative 1 over x is only for positive values of x, right? So this function 1 over x also exists for negative values, but it doesn't apply here for the natural log because it only takes in positive numbers. So there's a picture of the graph, right? So let's think about the relationship between our function, the red graph, natural log, and the derivative, which tells us slopes of tangent lines. So if I, whoops, here's a point. If I want, put it right there. If I want the tangent line to that point, let's look at a picture of it, right? It's a pretty steep tangent line, pretty positive. So it should be a large positive number, right? And we see that the value of 1 over x there is a relatively large slope of 2, right? If I get closer to 0, so I'm making that dot go closer, so there's as close as I can get with this resolution, 0.1, the slope is now 1 over 0.1 or 10, right? It's off of our screen here. If we scrolled down high enough, we see the value of 1 over 1/10 or 10, right? So as we get closer to 0, we see our tangent lines are getting increasingly steep. At the same time, 1 over x is getting increasingly large. On the other hand, if I go further to the right on this graph, our tangent line is getting flatter and flatter, right? I can keep moving out. I went as far as 10 on the scrolling bar. We're getting to a pretty flat line, which should have a slope close to 0. Well, if we're out at x equals 10, 1 over 10 is 1/10, which is exactly what the value of this derivative is. So it at least intuitively matches. Where our graph is flat, the derivative is close to 0. Where our graph is steep, the derivative is very, very far from 0, right? It's increasingly large. Okay, so that's it for this derivative. It's a pretty straightforward one, and we can use it exactly like we use all of our derivatives in combination with our other rules. So, for example, let's do the following function. Let's say g of x is equal to the natural log of the cosine of x. And I want g prime, okay? What I'm gonna notice is that I have a composition here. If I take f of x to be the natural log of x and k of x to be the cosine of x, then we see that f prime of x is 1 over x, k prime of x is negative sine of x, and the derivative g prime of x using, so this is f of k of x, using the chain rule is f prime k of x times k prime of x. And now I have, let's put all these pieces in, f prime of k of x should just be 1 over cosine of x. All right, so now putting all the pieces in place, f prime of k of x is 1 over cosine of x times k prime is negative sine of x. Let's give a little more space. And we can simplify this as negative sine x over cosine of x, which is, of course, the negative tangent of x. Right? So just a nice combination of this function with the chain rule. One other thing we should notice, there is a there's a problem with this function, or not a problem, but we should call some attention to something. Cosine spits out values between -1 and 1. Natural log cannot handle negative values. It can't handle 0 either. It can only handle positive values. So we need a domain here. We need to make sure we don't put in values of x so that cosine is outside of that, is spitting out values that aren't positive, right? So if you think about cosine, let's just draw a quick sketch. Here's 0. Let's do pi, negative pi. So at 0, cosine is up at 1. By pi, it's down to -1. It's also there at negative pi. Let's get these a little more even, something like that. I think I'm reading across correctly. Okay. And if I sketch it in, so it should be at 0, halfway in between here. So our graph should look something like this. Of course, I'm just drawing one period. It keeps repeating this, right, forever and ever and ever. So I can choose any of these, right? If I wanted to keep going, this becomes positive again over there and positive again somewhere out there. I can choose any of these positive or all of the positive intervals. You can have a domain that's broken up into sets. I'm just going to choose between here and here, right? This is pi over 2. This is negative pi over 2. So I'm going to take the domain for this function to be x between pi over 2, between negative pi over 2 and pi over 2, right? And I'm not including them because natural log can't handle 0. So let's take a look at this. Turn off all this guy. Here's our original function, right? So there on that domain, we see what it looks like. For instance, when x is 0, right? G of 0 is the natural log of cosine of 0. Cosine of 0 is 1. Natural log of 1 is 0. And then if we move in either direction, cosine goes from 1 to smaller and smaller numbers closer and closer to 0. Well, what does natural log do as we get closer and closer to 0? It spits out numbers that are increasingly negative. Let's look at that natural log graph again. Turn off all this other mess. Right, so there's the natural log function. As we put in x values closer to 0, it shoots down towards negative infinity, right? It just keeps getting smaller and smaller, well, larger in the negative direction. Well, now with our composition, as we put in values getting closer and closer to pi over 2 and negative pi over 2, then natural log is getting values closer and closer to 0, so it does what natural log does and gives us really large negative numbers. So we see this really elongated upside down U, or I guess like a stylish N. And then here is our derivative, negative tangent of x on that same interval, right? So on the right or the left side out here, I don't want to zoom, seems to want to zoom. Out here, if we imagine the tangent line, it's almost straight up, right? It's very, very steep and positive. And we see that tangent is spitting out very large positive numbers. Right here in the middle, tangent and this function spit out 0, and you can imagine a horizontal tangent line there. And then as we crest and go down the other side of the hill, we get very large negative tangent lines. And so tangent is giving us very large negative numbers. Okay, so it matches our intuitions. Okay, let's do 2 more examples. We'll just do some algebraic derivatives. I won't do graphs for all of these. Let's look at y equals the natural log of x over x, right? So I just want to practice combining this with other rules. Here we are combining with the quotient rule. So this derivative is going to be the derivative of the function in the numerator times the function in the denominator, minus the derivative of the function in the denominator times the function in the numerator, all over the denominator squared, right? That's our quotient rule. Well, the derivative of natural log of x is 1 over x times x, minus the derivative of x is just 1, so we just have a natural log of x, and we have this over x squared. And so 1 over x times x is 1, unless x happens to be 0, but we don't need to worry about x being 0. We already know this function we're looking at doesn't allow for x to be 0, right? Natural log can't handle a 0, the 0 in the denominator can't handle a 0. And so we don't have to worry about that. X equaling 0 is always already outlawed, so 1 over x times x is unambiguously 1, and we get this derivative. So again, we're just combining it with our other rules. All right, let's do one more thing. One more example. This is something that that becomes more useful when you get to other parts in calculus. So let's take a look at something right now. And it's always good for us to look at this kind of function. Natural log can only handle positive numbers, right? Sometimes that's not good enough. So we might decide we want to take the absolute value of what we input, right? This now can handle, the domain is now all numbers except for 0. Because we knew it could handle positive numbers, so we can certainly still put those in. We take the absolute value, nothing happens. But now we can put in negative numbers. We get the absolute value, gives the positive number, and we have and natural log can handle it, right? So in other words, what we're doing is we're extending wants parentheses. So that now we have the natural log graph that we're used to on the right, but we also get to put in negative numbers. We get the flip side of that, right? And it's got this asymptote at 0. If we zoom into 0, we see there's actually a bit of space there, right? Okay. So we've extended this function to include almost every number except for 0. So let's take the derivative of this, okay? We don't have a rule for absolute value. But what we do have is the definition of absolute value. Remember, absolute value is just a piecewise function. Right? It does nothing if the number you input is 0 or greater. It multiplies the number by -1 if the number is negative. So I can write this function as a piecewise function. If x is positive, I'm just doing the natural log of x, because if I put in 7, the absolute value doesn't do anything. So I just take the natural log of 7. On the other hand, if x is negative, like -2, then I take the natural log of -2 or +2, right, which is now doable. So we get this piecewise function, right? Notice I had to take off the or equal to for 0 because the natural log can't handle that, even though the absolute value could. So this means our derivative is going to come in piecewise, right? If I look at the derivative, if x is greater than 0, the derivative of f of x is the derivative of the natural log of x, which we now know to be 1 over x. But if x is less than 0, let's see what happens. We get the derivative of f of x is equal to the derivative of the natural log of -x. Okay, so this is a chain rule again, right? So let's try to do this one without writing out all the steps. We've done a lot of chain rules. We have the function with 2 functions here. We've composed the natural log with multiplying by -1, right? So we took multiplication by -1 and stuck it inside natural log. How do we take the chain rule derivatives with the chain rule? We take the derivative of the outside function, in this case natural log. We do 1 over whatever we've put in. So in this case, -x. And then we multiply this by the derivative of the inside function. In this case, the inside function is just -x. The derivative of -x is just -1. And so we end up with negatives canceling, and we just end up with 1 over x. And so it turns out we can actually extend our definition of the derivative of natural log of x to the derivative of the absolute value of x. Natural log of the absolute value of x is still just 1 over x. This isn't something we're going to use a ton of right now, but it does turn out to be a useful thing further down the road. So I just thought it might be a nice time to show it. Okay, that is it for this video. We're gonna move into we're going to generalize. We've done 2 videos now on natural exponential and natural log. What about when your base isn't e, right? Both in an exponential and in the natural log. And then we'll also see that this log, the derivative of the log, the natural log, gives us a really nice method for doing some other kinds of derivatives that would be difficult or impossible without it. So that'll be in the next video. This is it for this one. Thanks, everybody. I will see you next time.